We would like to do some calculus with our vector fields, but before we do that, we have to build up some notion of calculus on some related things, and then we'll transform that into an idea about calculus on the vector fields themselves. So this is 16.2 in Stewart's 6th edition. Let's assume that C R of t equals x of t, y of t is a smooth curve. So remember, that means that the derivative of r exists and is continuous. And smooth on this closed interval AB. So r prime is continuous and non-zero. That's the other condition. Now, if we subdivide AB into n equal width pieces, then we can do the kinds of things that we've been doing with integrals and set this up for integration as well. Now, what's this? I haven't actually told you yet. There is also a function of two variables defined over C. So let's let f be a function of two variables whose domain includes C. And I'm going to sketch the graph of that over here. So I have this curve C. Here's my curve C. It's a parametric curve. That seems to look something like this. There's my x and y axes. Okay, that's my curve C. And it's defined on some interval AB. So I have t between a and b. I plug this into my function r, and I come up with this curve in the xy plane. And then I take points off of there and I plug them into my function f, and I get some graph lying above the xy plane, and it may do something kind of this-ish. So the shadow of the blue curve is precisely C, but the blue curve is also going up and down in space. Now I'm going to subdivide AB into equal width pieces. But since I might be speeding up and slowing down as I move around the curve C, that subdivision does not necessarily result in an equal width subdivision or equal length subdivision of C itself. So I have maybe subdivisions like this, right? Speeding up and slowing down. Some parts I'm going faster, some parts I'm going slower. So where I'm going faster, I go a long way between these points. So say these are 1 second time intervals down here on the t-axis. Then up here in 1 second, I move from each point to the next. So if I move a long way in 1 second, I'm going fast. If I move just a short way in 1 second, I'm going slowly. So that's what it looks like. And I get this subdivision up here. Well, yeah, so I didn't do a great job of copying this, but we can deal. You get the idea, I think. All right, each one of those little subdivisions on C has its own width, which I will refer to as delta S sub I. So delta S sub I is the width of the ith subarc of C. And what I would like to do is find the area under the graph of F and above C. Okay. Can you see that kind of shower curtain? Well, I can actually see these, can't I? See that part. Can you see the sort of shower curtain? It's making this vertical curtain, but it's curvy. The top of the shower curtain can go up and down. The sides, though, are vertical. They just wind around so that they always lie above the curve C here. I'd like to find the area of that curve. Okay, so that's our goal. So I'm approaching this in the same way that we've approached half a dozen other things so far. I subdivide my domain, and then I will go and choose a sample point from within each subinterval. Oh, I should do those in a different color. I'll choose a sample point from within each subinterval. Somewhere. So each subinterval will have a sample point. That will correspond to some point here. And it'll give me some representative height on the curve. So if I use this sample point here, I get this height, and I will choose a little, not quite rectangle, but a little piece of my shower curtain that has a constant height on top, where that constant height is determined by the value of f at this sample point here. Okay, so that gives me an approximation to the area under the curve for just that one point. But I would like the total area under the curve, so I'm going to need to add up all those little pieces for each subarc of C. So definition. If f is defined on a smooth arc, smooth arc C, excuse me, smooth curve C, given as above by r of t equals the vector x of t, y of t, then the line integral of f along C, that whole phrase is what I'm defining, is integral over C f of xy ds, and it's equal to, well, let's see, I want to take my area under this little piece here, so that's going to be f of, it needs to be this xi star, yi star, but those come from the choice of ti star. So this is f of x of ti star, comma y of ti star, times delta si. So I go to the ith subinterval, I multiply by the length of my base here, and then by the height. Now it's not a rectangle, but it's a vertical surface that's a cylindrical piece, a piece of a cylinder. Not a circular cylinder, but the kind we talked about before in 12.5. So the area of it is still going to be the length of the arc here times the height, even though it curves. Right? It's still a base times height. And so here I have the base, there I have the height. That's the area of the one represented, or the one rectangle, not rectangle, the one piece of the curve here, or piece of the surface here that I've drawn. And then I need to add those all up. So I'll let I run from 1 to n, and that'll give me a really nice approximation to the area under my curve here. But I don't want an approximation, I want an exact value. So I will let n go to infinity. And as always, this is provided the limit exists. Provided the limit exists. Okay, that's our definition. And that will give us the area under this curve here. Now, you'll notice I've got this ds, right? My variable of integration is s, the arc length, which could be bad news, right? If we have to reparameterize whatever curve we're given in terms of arc length. That can be tricky. Fortunately for us, as is often the case, we have a really nice theorem that tells us how to handle this when our curve C is not parameterized with respect to arc length. So if f is continuous on C with the same setup that we've had here, then integral over C of f of x, y, ds exists, okay, and integral over C f of x, y, ds is equal to the integral, okay, this is nice. Let me pause here just a moment. Do you remember in all those triple integrals and double integrals that we were doing before, the trick, the part that we always had to figure out is what's the dA or what's the dV? Here we need to figure out what's the ds. That's what this theorem is telling us. So the ds, it's going to look like this. We're going to have f of x of t, y of t, well, y of t, times, now ds, given what we know about it, that s is this arc length function, ds ought to be related to the derivative of the arc length function, and in fact it is. It's going to be the square root of x prime of t squared plus y prime of t squared dt. This mess here is ds. And I think that's pretty reasonable because we can recall s would be the integral from a to t, this is s of t, would be the integral from a to t of magnitude of r prime of t dt. This should be a different variable, r prime of u du, say. That's how we defined arc length, the arc length function, s of t. And so using the second fundamental theorem of calculus, s prime of t is just the magnitude of r prime of t. So ds dt is magnitude of r prime of t dt. So ds should be magnitude r prime of t dt. And that's what we have here. This is the magnitude of r prime. And what it's telling us is this little bit of arc length looks like this. Well, I've erased my picture, of course, but I have this delta SI. That's the thing I have to figure out in my Riemann sum. Well, back this up a step. The delta SI, would be magnitude of r prime of t sub I times delta t sub I, which is just delta t. For some, I should say, magnitude r prime of t sub I star times delta t. For some t sub I star in the ith subinterval, there's a specific point where it comes out exactly right by the mean value theorem. So if we choose that to be our ti star, then we can replace the delta SI with an expression of that form. And then when we take a limit, it's just going to turn into this exactly, ds equals that. So it's the same process that we've done a bunch of times now. All right, so that's the ds. That's great. That gives us a way to evaluate these path integrals or line integrals. So I defined a line integral. I will also call it a path integral sometimes. That's the same thing. So we have a way to evaluate these path integrals without having to reparameterize in terms of arc length. We can just use the original parameterization in terms of t, and then compute the ds and go. So let's try this out. Let's just see what how this works when we actually try to do an example. So you have the theorem before you here. So you should go ahead and pause once I write up the example and give it a shot and see what you can do without my intervention. So here's the example. We're going to do the path integral over c of x ds, where c is the right half of x squared plus y squared equals 1. All right, did you pause and try it? If you got stuck, here's the first hint. You're going to have to parameterize that right half of that circle. So if that's why you got stuck, if you got stuck, and that's why, now that you know it, pause here, see if you can do it, and then see if you know what comes next. Here I go. Here's the right half of that circle. This is the circle x squared plus y squared equals 1. So I can take x equal to cosine t and y equal to sine t for t between minus pi over 2 and pi over 2. That'll take me from the bottom up to the top there. So now you have that parameterization. Do you know what to do with it? Pause, think about it, see what you come up with. Here I go. My parameterization looks like r of t equals cosine t sine t. So r prime of t is negative sine t cosine t. And the magnitude of r prime of t, which is the thing I need for ds, is going to be just 1. Square root of sine squared plus cosine squared. That's really nice because the radical in the integrand makes me nervous. Those cause problems. All right, so our integral then, integral over c of f of x, y, ds. Oh, I didn't write down the whole theorem. This should be as t goes from a to b. My limits of integration are just the, I've erased it now, are the endpoints of my t integral, of my domain. All right, so integral over c of f of x, y, ds is equal to the integral from a to b, which in our case is, where'd it go, minus pi over 2 to pi over 2, of f of x of t. So let's see, my f is just x, so I'm just putting in x of t, that's cosine t, and then times ds, which is a 1 dt. And that's great, we can integrate that. That integrates to sine t from minus pi over 2 to pi over 2, which is a 1 minus a minus 1, and so that's 2. So the area under this curve, x, and over this semicircle is 2. And let's look at a graph of this in Maple and see if that's plausible. I have set up Maple so I can give it my particular curve and points of interest, and Maple will graph it using a generic command of above. So here's the problem we're just looking at. Z equals x above a semicircle. We've got x is cosine t, y is sine t, f is just x. I'm going from minus pi over 2 to pi over 2. And then the rest of that is some kind of technical stuff that will get me where I'm going. So now my plotting command is up above here. I will graph f and some associated pieces that help me see what's happening. All right, first of all, looking at it from above, let's constrain the scaling here. Looking at it from above, I see my semicircle. And here's the surface I'm talking about. You see it? That's my shower curtain. I want the surface that lies above the semicircle and below z equals x. So I just get that red surface there. Whoa. I just get that red surface. Okay, this isn't a solid, it's just a surface. All right, that's what it looks like. Now, is an area of 2 reasonable? Well, let's see. This kind of looks like a triangle-ish thing, right? Looks like a triangle with base 1, height 1, but it's bent, and there's the other side as well. So let's see. Base 1, height 1, the area would be a half, and the other side would be a half also. So if there were no bending to it, my area would just be 1, a half plus a half. But we've got the bending that kind of increases it, so I expect the area to be bigger than 1. And sure enough, 2 is bigger than 1. On the other hand, this also looks like it's, if I took a cylinder of height 1, this is a portion of the lateral surface area. It looks like it's a quarter of it. Right? Half of it would be over here, but I'm only doing this semicircle, so I lose half of my surface area of the cylinder. But on the other hand, I gain half of it over here. Now it's roughly half. if I had the whole cylinder, then I would have the whole lateral surface area, 2 pi RH, with R and H both equal to 1. So I'd have 2 pi, but I don't actually have that, I just have this portion of it. Looks like, well, certainly if I throw out the right half here, I would get half of 2 pi, which is pi. And I don't get all of that. I get most of it because I have the big portion of the cylinder here. I lose the sides up above, but it's not cutting it exactly in half. So, but I expect my area to be smaller than pi. So it's somewhere between 1 and pi, and yeah, that's where 2 falls. Let's try another one. Let's try the path integral over c of x squared plus 2y ds, where c is shown. So here's c. I want to take a triangle. I'm going to go from 1, 2 over to 3, 2 and up to 1, 4. Okay, so those are the vertices of my triangle. Okay, give that a shot. See if you can figure out what to do here. It's a little bit different from the last one. So think about it for a minute. Here's what I'm going to do. First, I'm going to give myself more space because I don't need axes sticking out like that. This is in 3 pieces, so I'm going to have to break my integral up into 3 pieces as well. And I need to parameterize each piece separately. So this bottom piece here is the line y equals 2. Here's the line y equals 5 minus x. And here's the line x equals 1. I need to parameterize each one of those. Let me mark those as C1, C2, and C3. So to parameterize C1, I'm going to take, let's see, which one is, C1 is the vertical one here. So x is 1, and y is just y, but I'll let it be t. And then I need the interval. T will range from 2 to 4. And C2, this is a separate parameterization. It will be done in a separate integral, so it's okay to reuse values of t, just in case that comes up. This time y is 2, and x will range from 1 to 3, so I'll just let x be my parameter. 1 to 3. And then for C3, since I already have y as a function of x, I'll let x be my parameter. And then y is 5 minus t. And here, x is going to range from, looks like 1 to 3 again. It shouldn't matter which order I go. It shouldn't matter, my interval right now, if I do C1, C2, C3 in that order, I'm doing this. I'm going up here, over there, and then down there. And I'll add those pieces together. It doesn't matter, I don't have to go in a particular order because ds, remember, is the magnitude of r prime of t dt. So if I go right to left instead of left to right, that just changes the sign of r prime, but there's no sign change in the magnitude of r prime. So it doesn't matter how I do that. All right, so now my integral over c, my path integral over c of x squared plus 2y ds, I can break that up. This is a property of path integrals just like it is for ordinary single integrals and for double integrals and for triple integrals. I can break it up over non-overlapping domains. So I have integral over c1 x squared plus 2y ds plus the path integral over c2 of x squared plus 2y ds plus the path integral over c3 of x squared plus 2y ds. And I'm hoping that now you have enough to work with here where you can pause the video, run through that, and come out with what I'm about to come out with. Here I go. On C1, my variable is t ranging from 2 to 4. I have x squared, 1 squared, plus 2y ds. Oh, I didn't get my ds, did I? I need to get the ds. So if this is r, r prime then is 0, 1, and so the magnitude of r prime is just 1. On C2, r prime is 1, 0, so the magnitude of r prime is 1 again. And on C3, r prime is 1, -1, so the magnitude of r prime is the square root of 2. And I'll have to use those as I go here. So ds is the magnitude of r prime of t dt, so it's just a 1 dt. And then for C2, here it is, I have x squared, it's t squared, plus 2y, which is 2 times 2, times magnitude of r prime of t dt. And t is ranging here from 1 to 3. And then on C3, t again ranges from 1 to 3. We have x squared, where's my x? X is t. So t squared plus y, plus 2y, excuse me. It should be 2y. Times the square root of 2 dt. That's the ds in that case. And now it's just a question of doing these Calc 1 integrals. I have, let's see here, t plus t squared from 2 to 4, plus 1/3 t cubed plus 4t from 1 to 3, plus root 2 times 1/3 t cubed plus 10t minus t squared from 1 to 3. And what's that? 20 minus 6 plus 1/3 t cubed, so 9 plus 12 minus 1/3 plus 4 plus root 2 times, here's a 9 plus 30, that's 39 minus 9, so 30 minus, if I plug in a 1, I get a 9 from that, and a 1/3 to subtract off from that. And I'm not going to bother to simplify that. It's some number, but that's the area under this curve. So it's the area under the surface, x squared plus 2y, but above this triangle. So it's just the area under some sort of curve. So let's go to Maple again, and I will show you what this one looks like. This time, we have z equals x squared plus 2y and the triangle. So let me set that up. And now, here's what it looks like. And I see, hey, if I look at this from directly above, there's the triangle we're talking about. Here's my surface, z equals x squared plus 2y. Okay, nice parabolic cylinder. And then this red is the actual surface itself. You can see it. It's a vertical surface. It goes up until it hits the blue surface, and then it stops. So it's the red area is the area that we're trying to figure out. And you notice it's hollow, right? This is a surface, not a solid. This sort of curvy triangle on top here, that's the lid. That's the intersection of this cylinder with the surface of interest. And the area comes out to be whatever that number is. In both of these examples, we have to come up with the ds. That's the nature of these kinds of path integrals. So keep that in mind. Now, we can also do this same kind of thing with respect to x and y, it turns out. So I'm going to define a path integral with respect to x and a path integral with respect to y. These are different from the partial integrals that we were doing before. Path integral over c of f of x, y dx is equal to the integral from a to b of f of x of t, y of t, times x prime of t dt. So this x prime of t dt is playing the role of dx. And path integral over c of f of x, y dy is equal to the integral from a to b of f of x of t, y of t, times y prime of t, dt. And the y prime of t dt is playing the role of dy, as you might expect. Now these turn out, this looks like sort of a strange and artificial thing to do. These turn out to be really useful, and we'll see that a little bit later in the course. Now the reason these are not partial integrals is that x and y are not independent. When we did partial integrals, x and y were two independent variables, and z depended on both of them. Here, x and y are not independent because we're constrained to lie on the curve c. So if I change x, y is forced to change in some corresponding way so that we stay on the curve. Or if I change y, x is forced to change in some corresponding way so that we stay on c. So x and y are not independent. These are not partial integrals, and you have to be on the lookout for this. Okay. So these are easier to find because you just take the derivatives of x. You don't have to take the derivative of both x and y and then find the magnitude. But the principle is the same. I just need to know what the dx looks like. Now, what are these things? What do they represent? Well, if I think about what this really means, this is telling me that I want to take, when I'm doing Riemann sums, I want to take a width, delta x, and a height, f of x, y. So I have my curve in the plane, and I have my curve lying above it, doing whatever it does, right, some kind of shower curtain. And let me look at the dy integral because that'll be easier for me to draw here. So what I'm saying is I want to take, if I say I've subdivided this, I want to take my sample point and get a height here. The base I'm going to use for the height, though, is not going to be this arc. I'm not going to do ds times the height. I'm going to do dy times the height. So I'm going to, that's unfortunate. That looks like that's lying under the curve. The curve comes out of the board, right? It's not in the board. So this rectangle I have intended to draw back in the xy plane, or excuse me, back in the yz plane. But with a height corresponding to this height on the curve. So what it does is, it's kind of like taking my shower curtain and projecting it into the yz plane, just flattening it out. I'm looking at it this way, and what I see is a rectangle of this height. Not a curvy bottom here, just a straight bottom. And so I'm kind of getting the area that I would get if I projected my shower curtain onto the yz plane. That's sort of what this means. Now, that's not terribly accurate because, for example, if this thing curves back on itself and I project, then this part and this part will overlap, they'll cover each other up. And so I won't actually get the total area. I'll get something different. But what would really happen, I mean, if I'm thinking in terms of projection, what would really happen is, since I would get a dy that's positive when I come out the first part here, but a dy that's negative when I come back on this second part of the curve, there'll be some partial cancellation between the two. So it's not quite the projection thing that I was saying, but that's a way you can think of it when you don't have it curving back on itself. And it kind of helps you give some sort of geometrical interpretation for this thing. Let's try an example of this kind of path integral. I'll do the path integral of xy dx plus x minus y dy over c. And I want to point out, this is sort of a standard shorthand notation. I'm using two different differentials, but just one integral sign. And that kind of violates the premise that I've set forth before, that the integral sign and the differential should act as opening and closing parentheses. But this is the standard convention. This is how these are written. And c will go from 0, 0 to 2, 0 to 3, 2. So that looks like this. 0, 0, over to 2, 0, and then over to 3, 2. So there are two curves this time. All right, you have this definition. In principle, you know what to do at this point. Pause, try it out, come back and compare. Here I go. Let me call this C1 and C2 here. Now this time, I do want to point out, this time the direction I go matters. I'm supposed to go in this direction. And the reason it matters is the same reason that I get this partial cancellation between these two pieces here. Dx can be negative, right? The x prime of t can be negative if x is going to the left as t increases. That couldn't happen with ds because ds involves the magnitude of r prime of t. Dx and dy do not involve those absolute values, don't involve the magnitude. So they can be negative or positive. So I have to make sure that I'm going in the right direction. All right, so I parameterize this. Let's say C1 is given by, looks like x is what's changing, and y is fixed at 0. X ranges from 0 to 2, and t ranges from 0 to 2. And for C2, so for C2, I'm going to go back to our standard line parameterizations that we did in 12.5. I haven't been doing those for the line segments like on the triangle in the previous example, or this line segment, just because they're already so nicely described in terms of x or y. But now I'm going to go back to that old version. So do you remember how to do the old version? I need to take my final minus, that's a 2 there, that doesn't look much like a 2. I need to take my final minus initial, so that's going to be 1, 2, times t, plus my initial, 2, 0. Okay, so that's my parameterization. And let's see, for C1, oh, excuse me. For C1, dx is just dt, and the dy is 0. And for C2, dx is dt, and dy is 2 dt. Take the derivative with respect to t for the x and y components separately. And my path integral now gets split up into two path integrals. I get the path integral over C1 plus the path integral over C2. I'm doing a very shorthand here, so I don't have to rewrite all that stuff for both my path integrals. And this is going to equal, this is on 0, 1. So when I do this standard parameterization for the line segment, it's always on the interval 0, 1. Because when t equals 0, I'm at the starting point, and when t equals 1, I'm at the ending point, 3, 2 in this case. Okay, so my path integral over C1, that's going to be the integral as t goes from 0 to 2 of x times y, t times 0, dx, which is dt, plus x minus y, t minus 0, dy. There's C1. For C2, I have t ranging from 0 to 1, and I will have x times y, so x is t plus 2 times 2t, that's the y, times dx, which is dt. And then for the second integral, I have x minus y, so that's t plus 2, minus y, which is 2t plus 0, dy, which is 2 dt. And I will let you work out the rest of the details on that one. It's the setup I'm interested in right now. So does that all make sense? Make sure that you can do that and be ready to talk about it in class. And as you might expect, we can also do this same stuff in R3. I'm not going to do an example of that right now, but be aware that you can bump this up a dimension as well. Now here's a convention that we need. If C is, say, given by R of t equals x of t, y of t on some interval AB, then minus c, so this c is a curve, so minus c doesn't really make much sense as yet, but it's about to. minus c follows the same curve, but in the opposite direction. And the thing that I want to observe about that is that, what we've already observed, if we do the path integral over minus c with respect to x, that's going to be the negative of the path integral over c with respect to x. Because my dx will change sign, right? The x prime of t will be the negative of what it was for c. And path integral over negative c of f of x, y, dy will be negative path integral over c of f of x, y, dy. But the path integral over negative c of f of x, y, ds will be exactly the same as the path integral over c over c of f of x, y, ds. For the simple reason that ds involves the magnitude of r prime of t dt, so it doesn't matter which direction you're going. Now, I said at the beginning of this section that our goal is to do some calculus with vector fields, but that we had to do something related first. This is the related thing. Okay, now I want to figure out how to handle path integrals of vector fields. And so the idea is going to be to relate this new idea of path integrals of vector fields to this old idea, 20 minutes old at this point, but old idea of a path integral of a scalar function. So we're going to do this by thinking about work again. So recall, the work done by a force F over displacement d is W equals F dot d. Okay, that's our work formula that we developed back in section 12.3 when we first brought in the dot product. Now that's along a straight path. What if the force is applied along a curve instead? Let's take it as a curve in, let's take it as a curve in space. Here's x, y, and z. And I have some curve in space. Let's not get too fancy with it, but doing something. There's the curve c given by r of t equals x of t, y of t, z of t, say, on some interval AB. Well, we've parameterized here, so let me get my domain. Here's my domain from A to B. T range from A to B, and R will range from R of A to R of B. I'd like to know about the work done by a force F, by a vector field F, representing my force, in moving this particle from R of A up to R of B. The problem is that the curve curves, and we only know how to handle work when we're moving in a straight line. So what do? Think about it for a second. You know what to do. You know what to do because it's what calculus is. We're going to approximate the curvy thing with straight stuff. Yeah. Okay, so I'm going to subdivide AB into equal pieces. Those are equal for purposes of discussion. And that gives me a corresponding subdivision. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay? And let's say that here is my ith subinterval. So here is t sub I minus 1, and then there is t sub I. At t sub I minus 1, let's see, what is that? It's the third, okay. Let's call this point p sub I minus 1, and this point will be p sub I. Those are just the names of the points. Now, if I just draw a straight line between them, that may or may not represent what the curve is doing very well. The best way to represent the direction the curve is going is to use the tangent vector. Use a tangent vector. So I chose a bad spot for that. Let me pretend this one's pi minus 1 and here's pi. So here's my tangent vector. And I'm going to take the unit tangent vector at p sub I minus 1. That's the direction that I'm traveling when I'm at p sub I minus 1. And so that's the best approximation for what the curve is doing there. I'm going to take that as my displacement vector. Not actually the unit tangent, but that as the direction for my displacement vector. So what is the length of the displacement vector? Well, I need to move in this direction however long this little arc is. The length of the arc length. So this has some length, delta SI. And so the vector, my displacement vector, that I will use is d, we call it d sub I, equals delta SI times the unit tangent vector at p sub I minus 1. That's my displacement to get me from p sub I minus 1 to p sub I, at least approximately. And if my curve is smooth, which we will insist upon when we eventually write down a theorem, and my delta SI isn't too big, right, I'm not traveling too far, then that will give me a pretty decent approximation to the work done in moving, the work done by the vector field F in moving from p sub I minus 1 to p sub I. Now, I don't actually want to constrain myself to have to use p sub I minus 1, so I will choose just a sample point in here somewhere, and I will actually use the t from there. So I'm going to call this, instead of p sub I minus 1, I'm going to call it p sub I star. And now this will look like what we've been doing. So the work done by F in moving from p sub I minus 1 to p sub I is about, approximately, W equals F dot, well, one more explicit. W sub I equals F of, what do I call this R? So this is X of Ti star, Y of Ti star, Z of Ti star, dot delta SI times T at X of Ti star, Y of Ti star, Z of Ti star. Holy moly. Get rid of those things. Okay, it's that dot product. It's still F dot D. It's just that the F and the D are kind of complicated by the fact that we have something curvy going on. So the total work then is going to look like this. Right? I have to add up the work along each little piece. So I get capital F, I'm going to abbreviate this to Xi star, Yi star, Zi star, dot T of Xi star, Yi star, Zi star, times delta Si. There's my work for the one piece, approximately. And then I have to add those up. So I get the work for the whole path. And that gives me a really nice approximation to the work done by F in moving from R of A to R of B. But I don't want an approximation, I want an exact value. So I'm going to take n to infinity. And by golly, this is exactly a path integral. Right here, even though I started with vector fields, that there, because it's a dot product, that there thing, because it's a dot product, gives me a scalar. So above the red curly brace there, I have a scalar function times delta Si added up, and then I take a limit. That is exactly the path integral over C of F dot T ds. And so we have related this work to the scalar path integral that we did just a little bit ago. This is a complicated thing. Let's see if we can simplify it a little bit. This will be the integral from a to b. Right, we know how to do path integrals of scalar functions. I'm going to trade in the ds for a magnitude of r prime of t dt. While I'm at it, this t, that is r prime of t over the magnitude of r prime of t. And then the ds is a magnitude of r prime of t dt. And by golly, if that's not marvelous. Look at that. Cancel, cancel. Life is good. Not only do I not have the denominator to worry about, but I don't have that square root of x prime squared plus y prime squared to worry about. The radical that gives me so much trouble is gone. So this is just the integral from a to b of f dot r prime of t dt. And I will write that in the shorthand form as the path integral over c of f dot dr. So this is the work done by the vector field f and moving some particle from r of a to r of b. It's just the path integral over c of f dot dr. So we have two kinds of path integrals now. They're closely related because we come back to this same principle where my dot product gives me a scalar. But there are two kinds of path integrals we've dealt with now. There's a scalar path integral where we're just integrating a function, trying to find the area under some shower curtain. And then there's the path integral of a vector field, which looks like this, and reduces down to the scalar kind, but it means something different. Okay, if my vector field happens to represent a force, then I'm talking about the work done in moving along the path, the work done by the force in moving along the path. Now, this was specifically about work, but I don't have to be that specific. Now that I have this notion that the path integral like this of a vector field may be a useful thing, I will, as mathematicians always do, abstract that and express it as its own definition that we can work with as we need to. So let's let, this is a definition, let's let f be a continuous vector field on a smooth curve C given by r of t on the interval from a to b. Then the line integral, or path integral, line integral of f along C, I want to write path underneath here because it can be either one of those. I'll use the terms interchangeably. The line integral of f along C is path integral over C of f dot dr, and it is defined to be the integral from a to b of f of r of t dot r prime of t dt, and also path integral over c of f dot the vector t ds. Our motivation for this definition came from work, but let's look at a geometrical interpretation of what this thing actually means. That f dot t is actually a physically meaningful quantity. So remember from before that we can project one vector onto another. So here, f dot t over the magnitude of t, well, t is a unit vector, so that's really just f dot t. But this thing, remember, is the scalar projection of f in the direction of t. So what we're doing here in this path integral is we are finding the projection of f onto t. We're seeing how much of the vector field f is in the direction of t, and then we're multiplying that by some distance and adding those up. So we're adding up these projections of f onto t. We're seeing how much of f is moving in the same direction as t. Are they helping each other or not? All right, if f and t are perpendicular, then f is not contributing anything to the motion along t. If they're parallel, f is contributing a lot, in fact everything, to the motion along t. All right, I think it's time for us to try an example of this now, perhaps past time. Let's find the work done by this vector field, f equals negative y, comma x, comma 1, along the helix r of t equals cosine t sine t t, or on 0 to pi. So pause here, take a look at this and see what you can come up with. Okay, this turns out to not be hard to do at all. F on that helix will be negative sine t, comma cosine t, comma 1. And r prime of t will be negative sine t, cosine t, 1. And so the work done will be the path integral from 0 to pi of f dot r prime of t dt. Which is the integral from 0 to pi of, when I take this dot product, I get a sine squared plus a cosine squared, that's 1, plus another 1, that's 2. And so this is turning into a trivial integral to do, which is 2 pi. Okay, but it's just f dot r prime. These are very easy to do. So these aren't just about work. Let me show you another example here. This is from electricity and magnetism. This is called Ampere's law. And it says path integral over a curve C of B dot dr. So there's a vector field path integral. B is a magnetic field. C is some curve. Is equal to mu 0 times I. Mu 0 is a constant, and I is the current passing through the curve C. Here, C is some curve bounding a surface, so something like that. There's the curve. Ooh, there's the curve C. I is the current in some long wire. So there's current passing through the wire. And then there's this magnetic field that is produced by the current in the wire. B is not just any old magnetic field. It's a magnetic field produced by the current moving through that wire. And then there's this relationship. It's pretty cool. So this is not just this total abstraction or this weird idea that has no application. This turns out to be a pretty important principle, this idea of a path integral of a vector field. I want to make another observation here. What if we want to do something like this? Let's say f is given by p, q, r. So it's a three-dimensional vector field. And I want to find the path integral over c, some curve c of f dot dr. Well, if I just write this out generically, it's going to look like this. Integral from a to b of p, q, r dot r prime, dr is r prime of t dt, so this will be x prime, y prime, z prime, dt. And if I actually compute that dot product, I will see that I will have p times x prime of t plus q, and let me actually, that's x prime of t dt plus q, y prime of t dt plus integral r z prime of t dt. X prime of t dt is dx. So this is going to be path integral from a to b of p dx plus q dy plus r dz, where I'm using this convention again that when I have the dx dy dz with a single integral, it really means that there are three integrals going on. Oh, and I should change this back to a c now, actually. So this is the kind of place, when we do these path integrals, the terms we get are actually these integrals with respect to x or y or z, path integrals with respect to x or y or z. Again, not partial integrals, but path integrals. So it's not going nowhere either. Whoops, I did not draw this picture right. Yeah, I is supposed to pass through the surface. There we go. Sorry, I drew a random wire. I has to pass through the surface S. Okay, so let's do one more little example here. Actually, this one's out of the book, so let's look at it. All right, problem 18 says the figure shows a vector field F and two curves C1 and C2. Are the line integrals of F over C1 and C2 positive, negative, or zero? And explain. So this is the conceptual idea behind these path integrals. My vector field is kind of rotating around the origin in this counterclockwise way, it looks like, and it gets bigger the farther from the origin you get. Now, if I'm traveling along C1, I see, think of the vector field as actually like a river, right? And the current in the river is going the direction that the arrows are pointing. So the question is, when you're trying to determine whether the path integral is positive, negative, or zero, the question is the vector field helping you swim or hindering your swim? Is the current helping you swim or hindering your swimming? So here, if I'm trying to swim this way, I can't see, C1, it's traveling this way. If I'm swimming along this blue curve in this direction, is the river pushing me along or is it pushing against me? It looks to me like it's pushing me along, right? It's kind of going up over here and I'm trying to go down, but it's definitely going left and I'm going left. And over here, it's going down, which I am, and it's starting to curve back to the right, which I am also doing. So on C1, my path integral should be positive. Okay? The vector field is helping me swim. The projections of F onto my curve are mostly positive. They're mostly going in the same direction as the vector field. On C2, let's see now, as I go up at the beginning here, the vector field is also going up, so that helps. And it's kind of going toward the right, at least for a while, until back left up here. But I'm getting a little bit of help at the beginning. When I reach the top, though, and I'm starting to come back down, the vector field is opposing me. I'm trying to swim upstream at this point. There's some pushing me to the right, which I want, but it's mostly opposing me. And the big arrows are over here, where I have opposition. The small arrows are over here where it's helping me. So it's helping me a little at the beginning, but it's hurting me a lot at the end. And so this path integral should come out to be negative. And if I traveled in the other direction, it should come out to be positive. All right, there's a lot more to do with these things. They're really interesting, and there's a lot of cool theorems and cool applications we can do. So think about these really hard, see what you can come up with. Make sure you understand what we're doing, and come with questions. I'll see you in class.